Good morning, good afternoon, good evening. My name is Bob Plankers, and today I often talk about security and compliance topics in VMware Cloud Foundation and VMware vSphere. And today's no different. We're going to talk about confidential computing and what that means here moving forward. A couple of disclaimers. I may talk about the vision and the roadmap a little bit. So there's that, and the disclaimer that I always talk about context. That the context of your environment, when we talk about security best practices and ideas and things like that, we're talking generically. We don't know your environment. And so, whether the stuff is appropriate for your environment or not may differ. It might be too much, might be too little, but that's for you to decide. And if you need help figuring that out, we're happy to do so. Our professional services folks, you have access to them as a VCF customer. And let us know what we can do to help you in these regards. When it comes to environments and environment security, most everything in computing nowadays, as far as security, comes down to a problem in trust. All breaches come down to abused trust. Most notably that you've chosen to trust something and that trust relationship is now being abused by an attacker. VCF is all about trust, or rather the ability to not have to trust so much. You're the one making the decisions about where your data is, where you think it is. Wherever you put data, that's where it stays. I get asked from time to time about data sovereignty in VCF, and that's really your policy. Data will stay wherever you put it because that's the nature of it. You can trust that only your own organization is changing it. You can trust that only the people that you've granted access to your systems actually have access to your systems. And I know organizations are complicated and that trust inside of an organization can be weird at times too, but it's different than a public cloud, for example, where you've got a lot of inherent trust that you're required to accept. You have no choice except to go with it if you want to use those environments. You can verify in VCF. Part of trusting, this idea of zero trust is we want to get rid of trust. We're actually really trying to get rid of trust in VCF by replacing it with data, current data. And so we can use VCF Operations on a recurring, it'll check every hour periodically to see if the system is verifiably secure. Has something changed? What changed? And should I highlight that as a problem? Should I bubble that up to an administrator? Hey, somebody went and changed the security setting on one of the hosts. In my past life, that was usually me. I was troubleshooting something and I forgot to put it back, but could be an attacker, could be whatever, and get somebody to get in there and take a look at it, be able to drill down in the audit logging and then come to a resolution, either automatically through technologies like SaltStack and the VCF Operations, being able to remediate that direction, or just manual intervention as well, however you want to do it. And so, trust, very important. And so when we think about trust and how to avoid needing trust, we think about data mostly. Three states of data that exist, or data exists in these three states. It's sort of like liquid, gas, and solid. Data at rest, data in transit. Data at rest is sitting in a storage device somewhere. Data in transit is moving across the network, and we can mitigate trust issues with those things. If we're using external storage, vSAN brings that trust all the way in, and we can trust ourselves. vSAN's got great integrity protections and really easy to use encryption, data at rest encryption. But that's the thing. Encryption, even over the wire to an external storage array, encryption is how we mitigate trust issues there. And same with data in transit. We use TLS and similar network encryption techniques to mitigate trust issues. The fact that we don't really want to have to trust the network. We assume that the network is spying on us and we don't want our data to get out. And so that's how we deal with it. But there's this third state of data called data in use, where we're actually using these things. CPU and memory and hardware in general make a lot of promises about the security of your data while it's in memory, well, it's in the CPU registers and things like that. But back in 2018, we discovered, some security researchers discovered that those promises aren't kept all the time. And CPU vulnerabilities, Spectre, Meltdown, and then later on L1TF and MDS. And there's been variants of all of these stuff, all of these things, up until recently. There's new versions of this coming out all the time. And they really illustrate real problems in hardware. And hardware is hard because hardware, once it ships, you can't just update it like you can software, and so these are structural problems in many cases. And and so in hardware itself, we see basically three types of trust issues. First, these vulnerabilities, just straight up. Hardware, CPU and memory controllers, other hardware devices allow for leaky boundaries. Two workloads that should never be able to touch somehow can, because they've abused hardware to do it. It's not something that we can prevent necessarily in the hypervisor, though we do have some ways of changing CPU schedulers, for example, to be able to avoid certain situations where that might be the case. Second, in a shared environment, you don't know who your neighbors are, and you don't know the state of vulnerability remediation in hardware. And so on premises with VCF, you own the hardware. You're the tenant of that hardware, and you know who your neighbors are. It's you. Maybe. I know there's shared environments and all that stuff, but in general, most of our VCF customers own the whole stack from the ground up, and they know exactly what your firmware level is, what's remediated in that firmware level, all of the way up. But that's not the case in other environments, public cloud, for example. And those neighbors get to your data by abusing an unmitigated vulnerability in hardware. And then last, privileged access. And this affects everyone. There's always a certain level of trust you are forced to accept in a hosted environment, in a shared environment. And that's usually the VCF admins, people like myself. The VCF admins have a lot of power. And this, again, it's largely mitigated by the control you have over who has access to the environment. You can control that and monitor and manage that. But still, in a VCF environment, this is the same as the public cloud. Basically, you have to trust the people that run the public, or not the public cloud, but the infrastructure itself, the platform. And so the big question comes up in a world that looks at things and wants zero trust. And zero trust is hard for a lot of organizations, and because it requires less trust, not more. And it requires having hard conversations about boundaries and maybe doing some things different. That old, that's not how we do things around here, or we've always done things like that, those sayings. In the face of new security threats, we need to evolve. All of the defensive side of security needs to evolve too. And so how do we mitigate these things? And that's where confidential computing comes in. Confidential computing at a very high level, you can think about it kind of like, I've used apartment building metaphors before. You can think of it like maybe a hotel safe in traditional setups. Hotel safe, you can lock your valuables in the safe, but the staff of the hotel still has a way to get in there if they wanted to get in, if they were untrustworthy in some way. And sometimes this happens, but if they were untrustworthy in some way, they can open your hotel room safe with a master code. And so you have to trust them. You have to trust all of those people, and you don't know whether they're trustworthy or not. You're taking it just on faith. Whereas with confidential computing, the analogy would be a storage unit. You've got your own padlock on the storage unit, and only you have the key. Certainly, somebody else runs and maintains the whole building, but you don't have to trust them as much. Somebody can cut the lock off. And confidential computing, there's various attack vectors, and we'll talk about that too. There's some new ones, in fact, that involve hardware in a data center, and so physical security can be important too. But in general, with the storage unit, you don't have to trust the facility staff so much. And that's what we're going for in these on-premises environments, or, in the cloud as well. The ability to not have to trust as much and just use verification, continuous verification, like I was talking about before. So let's talk about ESX. ESX has got a bunch of security boundaries inside the hypervisor, and it starts with the guest operating system itself. And unless you're running an old operating system, which is still possible on even VCF 9, like Windows 3.1. Windows 3.1, Novell NetWare back in the day didn't have per process boundaries, but those are gone. And 3.1 still runs. You can search the internet for my experimenting with that, and OS2 Warp, for example, but still runs just fine. Should you do it? But the Windows Server 2025, something modern, Linuxes, all of that stuff have per process protections. They've got role-based access control. And these are really powerful protections against attacks that come into the applications themselves, the workloads themselves. The next step around the VM and the guest operating system is really the VM runtime, or the container runtime too. There's two different runtimes there. And that is what, if you log into ESX, that's what you'll see on the process list. You type PS and you'll see all the processes. And you'll see the different VMs running as processes there. And those are the VM runtimes or container runtimes. And that's a security boundary too. And around that, to prevent VM escape, and we'll talk about that in a minute, is what we call the sandbox. It's a mandatory access control designed to detect. So we know what the VM runtime should be doing and what it shouldn't be doing. And if it tries something that we think it shouldn't be doing, the sandbox shuts it down, detects that, and says, hey, there's a problem here. And so a powerful defense there. Not perfect. There are ways through it, and we see security vulnerabilities. From time to time, we make advisories about that, and we patch, and that's the solution to that. And we've made patching a lot easier so that we can deal with this, especially in VCF 9 with live patching and all of that. So each VM, each workload, container workloads as well, get these protections, and they all sit on ESX. ESX itself is a security boundary there too. You can have different security settings on a per host basis. We don't necessarily recommend it, but you can, and certainly on a per cluster basis, you can make different decisions. We kind of recommend that the hosts inside a cluster are kept as similar as possible, but that's not always necessary or required or even desired in some cases. So, and then underneath this, CPU and memory, of course. And the protections that they promise, what they offer, or maybe not, And so we've got, we've got trouble there. And so how do we prevent that? Well, let's talk about AMD and AMD's implementation of some of these technologies. Back in vSphere 7, we introduced support for Intel's SGX and AMD SEV-ES, which brought with it the idea of a trusted execution environment, or TEE. And these trusted execution environments are self-contained, encapsulated, encrypted things on these hosts. And so now in VCF 9, we've extended that to Intel TDX and AMD's SEV-SNP, the follow-on technologies to those original ones. SGX was a per process technology as well, and not a per VM technology. The newer versions of these things were per VM. It can help you protect the whole VM. And so a trusted execution environment, is basically the storage locker we were talking about in my metaphor analogy earlier. So AMD and Intel have different approaches to this, and Intel uses more of a logical separation inside their chipsets. AMD uses more physical separation in there. And to that end, AMD, I'll talk a little bit about AMD's implementation, not to play favorites or anything here, but it's interesting because they've embedded a security processor in their EPYC CPUs. And it's actually an ARM Cortex-A5 CPU that rides along in the same die. You don't have to license it independently or anything like that. It's just part of the EPYC CPU. And its purpose is to be a gatekeeper. Its purpose is to issue encryption keys and also check integrity and attestation, run the attestation services there. And so when a VM wants to participate, and your guest operating system has to be able to participate, what it'll do is it'll request an encryption key from the platform security processor. It'll go through the attestation process to verify that it's that the configuration of the host, configuration of the workload is in a known good state, and Yeah, and then the data is only decrypted when it goes to run. It's still encrypted in memory, and it's encrypted in the CPU registers itself. And so that's really interesting. That's a lot a lot of protections there. And so each VM can get this if it wants, and it's not an all or nothing thing. A guest operating system can choose not to participate, or maybe it can't participate. Maybe it's old, or maybe you don't want it to participate. This stuff does add some complexity to the environment, and maybe you want to just do this for your tier 0 really important workloads, that sort of thing. But if there is a future hardware vulnerability, and there probably will be, being completely honest, and AMD's been pretty forthcoming about this, like there's going to be stuff that is unknown that researchers are going to find, and then we'll fix it in as we go and can. But if you can abuse these hardware vulnerabilities, all you'll get back is the ciphertext, the encrypted text of whatever. You're not going to have the key. It's really hard to get the key back out of the PSP, for example. And so that's interesting. That's some pretty powerful future proofing against possible future vulnerabilities, while also establishing trust in the environment if you'd like to do that. And so these are pretty advanced workload security protections. One of the things to note is the hypervisor is not granted access to it doesn't share the secret. So the hypervisor can still manage scheduling of workloads. It can still allocate memory, make device assignments and things like that, turn it on and turn it off. I mean, that would be pretty bad if you couldn't control that sort of things, those sorts of things. But beyond that, it's up to the workload to share information with anything else and to authorize that. And so the VM can choose to share memory pages or pair of virtualized devices or whatever with the hypervisor. And so that's an important thing here. So AMD SEV-ES and SGX didn't offer the capabilities to share like that. And so you basically lost snapshots and vMotion and all of that. And so that becomes an operational consideration. With TDX and SEV-SNP, the possibility is there as part of the vision moving forward. And I'll talk about that in a little bit here. There's additional integrity protections. This attestation I was talking about is one thing, but above and beyond that, integrity protections against things that the hypervisor can do. And so hypervisors, basically otherwise can see the internal structures of your data in memory. And it's like a book. The hypervisor might not, in some of these encrypted cases, SGX and SEV-ES, the early versions, they couldn't read the book, but they couldn't read the words in the book, but they could rearrange the pages of the book, and that's not good either, And so these new technologies help prevent that. They also include protections against devices, DMA, device direct memory access, DMA, where a device can write directly into memory, and that's a real performance savings technology there, or performance enhancement, where a CPU doesn't have to get involved for data transfer, for networking and all that stuff. But you don't want those devices to be able to manipulate data inside the TE, trusted execution environment either. And so important there. And then that attestation that I was talking about, the cryptographic proof that the code that you think you're running, the VM itself is the VM that you think you're running, and cryptographic proof that the platform that you're on is the one you expected to be on too. And so all this stuff is evolving. There's a number of attacks here, and this is a kind of a eye chart here. It's definitely a chart, but it's interesting seeing all. And this is not, by no means is this a complete list of all the different attacks that are available. In fact, one has surfaced recently where people invented hardware that they could put between DDR5 memory and the system bus and an Intel and the memory bus, the memory socket, and it's basically an interposer there, and they can read and recover TDX keys and things like that. And it's a physical attack, and physical attacks, that's why physical security is important in these environments too. They've got a suitcase looking device that can do this in a rack. And so it makes you think, makes you wonder if in your data center somebody would catch that sort of thing. But so these technologies solve a number of them, but it doesn't solve things like active RAM corruption, the row hammers, and things that manipulate the DDR bus, like I was explaining here. It doesn't solve that, but it solves a number of other problems too. And so just kind of elevates everything, raises the bar a bit. One of the most interesting things on this slide, though, is at the bottom, secure migration support. And this is evolving. The AMD and Intel helping us figure out how this is going to work, moving forward. And so SEV-SNP has got some capabilities in what's shipping now. And we've got on our roadmap to support that in a future version. That's part of our vision. But TDX, that's still being worked out as part of how they do their stuff. And so more to come there. But it's an exciting space. It's a new space. And like I said, it's evolving all the way around in the industry, and we're coming right along with it too. So to recap, basically, started a while ago, and is evolving. AMD's SEV-SNP, Intel TDX offer some much deeper protections than their older counterparts. But you can turn on some of these things right now too. Confidential containers is a great use for AMD's SEV-ES if you've got that capability in your hardware. So one of the things, you might not have vMotion, but the Kubernetes functionality in VCF does not vMotion. It instantiates a new copy of everything and then terminates the old one. So it doesn't vMotion containers and workloads like that. And so it can use this stuff just natively. And so it's the confidential containers is a flag in your YAML file. So you can use it right now and raise the bar a little bit for almost no operational cost whatsoever. And like I said, a rich roadmap moving forward. If you'd like more details on that, please reach out to your account team who can hook you up with the product management staff, and we can talk with you about what you need, what you're looking for. As we wrap up here, my perpetual request to sign up for security alerts. If you're not getting email about security advisories and things, if you haven't gotten one in the last 6 months or so, you should probably check to make sure you're signed up still, and just Google search for VMware security advisories. You'll find this page, and there's a button right there. And then we've got a nice GitHub repository with all kinds of Q&A and resources for defenders, people looking to secure their environments. Our hardening guidance is out there. You can use a QR code. The QR code, if you don't like QR codes, I get it, kind of, but it goes to a redirector, so I'm doubly evil in this case. And that's actually a bit.ly redirector, and then it goes to GitHub. You can just go to GitHub and search for security, and you'll find it there too. So with that, I thank you very much. I appreciate you and what you're up to and trying to be secure, and I wish you good luck with that. Let us know how we can help. Thank you.